So for those people who aren't attending today and watching the recording, welcome to tutorial 10. And those of you attending today, yeah, welcome to, this is going to be our last tutorial together. So, yeah, it was neat for me because this is the first time I taught this course. So, yeah, I had a good time. Thank you for attending. And I know you didn't technically have to, so I appreciate it, and I appreciate the questions that you brought. And yeah, for your attention. So, announcements. Problem set 3 is due on December 6th. I think it should be available, but if it's not, it should be available this week. And then this is the last tutorial. Hello. So, but there will be some self-guided resources posted for the last 2 chapters. We had like a discussion about it, and I think it was just like traditionally this course only went up to tutorial 10. Tutorial slides from link 4. Yeah, I can repost it. Yeah. I'll do that after. Okay. Okay, I guess some content review then, same as always, and then yeah. So last week or like finishing up chapter 9, we talked about sort of this band theory. So as atoms approach each other, the energy levels begin to spread out, and then these differences between these energy levels become smaller as the number of atoms increase, and then we form this sort of continuous band, like sort of shown in the figure in the textbook here, where if we just slowly start to increase the amount of atoms, we're sort of building up this bar that we see here. And this is the case in our solids as we deal with many atoms, and this band is essentially continuous, and promotion can take place in this continuous band. So for the example of copper, we remember copper has an electron configuration with argon 3d10 4s1. Therefore, when we have a large amount of copper atoms, we can accumulate the sum of those 4s energy levels into a band as shown in the previous slide. Sort of, again, this accumulation, summation, and then since the 4s atom only has one electron, is half filled, and therefore is expected that the band structure appears like this figure, where we have a half filled state. It is easy to promote an electron from its filled state. And then a similar principle is shown in aluminum with an electron configuration of neon 3s2 3p1 would have a filled and empty portion of its p valence band. Then we have magnesium. Magnesium is just 1 proton less than aluminum with an electron configuration of neon 3s2. As we can see here, magnesium has a completely empty 3p band, and that is why it is not written in its electron configuration, but it is still there. And in previous discussions, I think I mentioned it in like the last tutorial, where we had like this example of like a 4f band or 4f orbital, and if the lanthanum was 4f0, so we just don't write it, but it's still it still has a 4f orbital. So sort of similar principle here, we're just not writing it, but it technically does still have that opening. And so these 3p band overlaps with the 3s band and allows for promotion of 3s electrons into this empty 3p band. And this overlap allows a magnesium to still act like a metal. And then we have ceramics and polymers. Ceramics, they're held together by ionic bonds, which involve electron transfer. and this leads to a filled valence shell and no electron energy states adjacent to these filled states. There are no free electrons in the system as well, unlike the electron cloud in metals, as they are tightly bound to their atoms. In polymers, we have covalent bonding. The valence electrons are shared between atoms and are tightly bound. Therefore, both types of materials are insulators with the associated band structure seen in this figure. The band gap is the forbidden region where electrons cannot exist, and because they're quantized. And this band gap would be sort of like these half or quarter sort of states where, you know, you would have n equals to 1.5 or 1.25, something like that, where it doesn't exist because they have to be integer values. And then for these insulators to conduct, we would have to provide so much energy that it promotes over this band gap into the conduction band, and thus they can freely move. So technically, with some of these, you can make an insulator conductive. It's just a matter of you'd have to put so much energy in just to promote one electron, and it doesn't become feasible because, again, if we're just take so much energy to promote one, then imagine like 10 to the 23 electrons, right? So sort of why they stay insulated. And then we have semiconductors. So semiconductors have a similar band to insulators, although the band gap is a lot smaller, meaning we can provide a certain amount of energy to control conduction or insulative behavior. And this is why it is called a semiconductor. And they are intermediate states between conductors and insulators. And that's sort of shown in this figure here, where it just has a smaller band gap. So it gives us more control, and it's a little easier to do that promotion. With some photon interactions. When photons interact with metals, it is easy for electrons to be promoted to higher energy states since there is no band gap. When the electrons relax to lower energy states, they re-emit the incoming photon, and that creates that shine on your typical metals. If a material has a large band gap, incoming photons will not have enough energy to cause electron promotion over that band gap. Therefore, they're just passed through the material. That's sort of what happens with some of these. If you think of like a diamond, let's say, which has a really big band gap, so light can just pass through. And now we're talking about hybridization. Everybody good with the material before start skipping ahead? Just don't want to rush through everything. We still have lots of time. So. No? Okay. Silicone and sp3 hybridization. So silicone has an electron configuration of neon 3s2 3p2. And as we can see, this makes up 4 valence electrons, 2 in the 3s and 2 in the 3p. And these are the ones that are involved in bonding for silicone, although a problem arises since they are technically at different energy levels. So what we sort of have to do is change the model to accommodate this. So if the S and P orbitals are combined, we can define and form a new hybrid orbital in one matching energy level, and this is known as our sp3 hybrid orbital. And this solves the different energy level problem. And then this is sort of our our crystal structure for this. So since now we have 4 identical electrons, these systems will have a tetrahedral configuration of equal spacing. That's sort of shown in this corner here. If we consider the crystal structure, it will make up this diamond cubic structure with these tetrahedral configurations within. And this structure can be thought of as an FCC with the same amount of atoms occupying half the available interstitial sites. And then we have intrinsic semiconductors. So all electrons are bound to their atoms. When we introduce a voltage, we get some promoted electrons. When an electron is promoted to a conduction band, it leaves behind a broken bond, and the promoted electron leaves behind a hole, as seen in this figure. And this type of semiconductor is called an intrinsic semiconductor, as we are promoting electrons from its internal structure, and we're not inputting any electrons into the system. We can calculate the conductivity through the equation where it's sigma equals nq mu n plus pq mu p, where n is the concentration of promoted electrons, number of electrons per volume, p is the concentration of holes, q is the charge of electrons, mu n and mu p are the electron mobility and hole mobility expressed in meters squared per volt times second. We can promote electrons in a variety of ways. In intrinsic semiconductors, you can do it through temperature changes, which has an Arrhenius dependence, which we may have seen before, which is sigma e to the Eg over kT, where Eg is sort of that promotion energy. And then we can also excite electrons through photon energy absorption. If we absorb energy larger than the band gap promotion will occur. And for instance, in silicon, its band gap is 1.1 eV. So absorption is higher than this energy will promote electrons. And photon excitation leads to electron hole pairs in silicon. So if we apply an electric field across silicon, we can actually see an electric current. And this figure here is just sort of temperature effects on this sort of promotion energy. Extrinsic semiconductors involves the addition of dopants into a system to control their conductivity. The dopant overpowers any intrinsic semiconduction, and that is why it's called an extrinsic semiconductor. We dope by adding electrons into the system. We call it an N-type semiconductor. N for negative, since we are adding electrons, and then if we introduce holes into the system, we call it a P-type semiconductor. P for positive, since we're removing electrons. And we introduce these impurities through point defects. So we'll start with N-type semiconductors. The instance of silicon, which has 4 valence electrons, we can introduce something like phosphors, which has 5 valence electrons, which will introduce 1 extra electron into the system if we just sort of place it in this sort of silicon cloud we have here. And this 1 extra electron is freely bound, can be easily promoted for conduction. Small amount of energy is required to donate this extra electron into the conduction band, and therefore N-type has a donor energy level. That's sort of represented with this little blue line here. And since the dopant contributes a lot more to the promotion than the intrinsic component, when calculating the conductivity, we can calculate only in terms of electron mobility and concentration. So we sort of remove that whole second term. Again, because this is like usually 2, 3, 4 times higher magnitude than the other components, so we can assume the other one just has no effect really. P-type semiconductors, if we dope silicon with a boron, we can introduce a hole into the system, and this is because boron has only 3 valence electrons, and therefore there will be 1 broken bond or a hole for every dopant atom, and that's sort of seen here. Since the hole is now a place where an electron can promote, we call this the acceptor level, is located in the band gap down here. And in a P-type semiconductor, we can calculate the conductivity based on the holes being the charge carriers only. So in this circumstance, the holes are going to have a lot higher conductivity sort of contribution than the dopant. Ionic conductivity, I know this was something that was not really covered too much in the textbook, like it just had a little paragraph, but it occurs with the movement of ions within an ionic solid. So I just want to give like an example from my work. So for example, in my project, the gels I work with have acrylic acid, and we partially neutralize this with sodium hydroxide. It introduces this partially neutralized hydroxyphilic acid that has these sodium ions in the system. And this is important since for swelling, the repulsive effects of ions causes the gel to swell during water absorption. Inherently, since we have an interwoven gel covalently bonded, it is not electrically conductive, but it is ionically conductive and exhibits capacitive behavior. So because of these ions, it sort of features this ionic conductivity, and therefore we can sort of hold electrical charge in sort of our gel and on one side of the gel. And so for my purposes, this is good since it allows the gel to swell, but charge just builds up on the surface of the battery rather than transmitting through. So that's just sort of an example of ionic conduction. Any questions from content? If not, we can go to the quiz. So I sent out the quiz. I think it's only a couple of questions. Let me know if you don't have the quiz. I can send the file in the chat if anything. Let's see. Okay. Yeah, there's 5 questions, so 10 minutes, I think should be enough time. The last 3 are sort of just word things. The first 2 are calculations. So let's say until 1:38. Okay, I guess that's time. Any questions? There's only us two again. Here are the answers. Yeah, for sure. We have a lot of time, so yeah. One. We have not kind of bad, but oh. Mhm. And four. What is the intrinsic conductivity in the one? Okay. So we have to use this equation. Here, we can copy and paste it. Okay. Q is the charge of an electron. Cool. And then I guess we just don't know the carrier concentration. Um, and as units of number of electrons per meters. We'll come back. We'll do some examples and we'll come back to it because I just didn't write out these two word problems. But for 3B, 3, 4, 5. So 3 is which of the following statements is false? So we got B. So if we remember from 2 tutorials ago, so if we have, this is 3, says that ceramics have a directional ionic bonding which makes them opaque. And I pull up, I think it was tutorial 8. Well, they have directional ionic bonding, but it's not the direction that makes them opaque. It's rather that we have that large band gap. that we have to cross over. And since we have an incoming photon, it can't excite over this band gap. So what happens is that it wait, no, that's not right. Hmm. Okay, yeah, that's what it is. The keyword was they're non-directional. I was looking for that in the other slide, but I guess I didn't write it. And then B says that ceramics have directional ionic bonding, but it's non-directional. And then 4, why is diamond optically transparent while silicone is opaque? And that's this. So diamond, large band gap. So photon passes through, while silicone has a much smaller band gap. So when a photon comes in, it promotes. So that's the answer to C. Diamond has a high band gap 5.5 eV, while silicon has a moderate band gap 1.1. Since visible light photons have energy within 2 to 3 eV, they can excite electrons in silicon, but not in diamond. Two to three eV. 2 to 3 eV. Okay. And then 5. Regarding extrinsic semiconductors, which of the following is false? That one we have to look at the periodic table. We have gallium and germanium, they're right beside each other. But it says germanium doped with gallium is N-type. But since we look at the periodic table, gallium, germanium, and since gallium is behind germanium in the periodic table, has 1 less electron. So then if we have sort of our atoms like this, let's say this is our gallium, then it wouldn't add an electron, it would be missing an electron, let's say here. So then you wouldn't have N-type, but you'd have P-type semiconduction. Okay, P for positive, and then which means that there's a hole or like electron missing. Okay. Yeah, not everything is a semiconductor, right? So it's like some things are gonna be compatible with others. Like your typical semiconductors are usually on that right hand side of the periodic table. So like aluminum, like silicon, germanium, gallium, like sort of those things. Um, there's usually like a compatibility thing. Obviously, you're not gonna add in something that's like completely different because then it's like it might not stabilize. Like you usually want to choose something that's fairly close because you kind of just want to change the structure enough that you're only changing it by one electron or so. Because if you start adding too many things and you're sort of changing the whole stability of the structure and you might not even end up with the what you're thinking that you're going to end up with. So it's like you change it too much basically, then you might not even form a product. Yeah, they left during the quiz. Okay, we'll do some sample problems and then we'll go back to those quiz questions. So sketch the generalized band structures of conductors, insulators, as well as intrinsic P and N-type semiconductors. No, it's in the slides. So if you literally just go back in the slides, you can find it and just draw it on the whiteboard and I can put it on the slides. Then we can sort of go through it. So our draw out like the so this would be conductor. Okay, fill in the first one. Let's say that's a conductor. Yeah. And then that's an insulator. For some reason my pen doesn't want to work. So then we have band. There's a band gap there. It's in the slides that it's usually 4. Is to be greater than 4 EV. Okay, so then intrinsic. I don't know why it doesn't want to write. P type and then N type. So what does an intrinsic? Yeah. Yeah. And what's the difference between that and the insulator? Just look at the middle of the insulator and its band gap. What would the intrinsic have? An insulator has, yeah, yeah. Okay. Yeah, that's, yeah, less than 4 eV. Yeah, so I'll just draw it out on the slides. We have conductor. This would be a conductor. We have an insulator. And that's our band gap. And conduction band. And a valence band. And okay. Okay. So that's our intrinsic. And we have this is their P type. It has an acceptor level. And then their N type. And it has a donor level. It still has these valence and conduction bands. Okay. Okay, question 2. Following characteristics are for both intrinsic and P-type extrinsic gallium antium at room temperature. On the table, sigma is electrical conductivity, N is the concentration of electrons in the conduction band, and P is the number of holes in the valence band. So it gives us these values here. Conductivity, like resistivity, can have many different units. For example, since ohm is the inverse of Siemens, we can write conductivity as Siemens per meter. In order to relate the units of the different variables presented on the table, start by demonstrating the relation that ohms is volt seconds per coulomb. So we remember from high school, V equals IR. We're just gonna change this to V equals A for current and our ohm resistivity. So we have A is current, and then ohm is just our resistivity. And then if we think about, let's say, a wire, and we have our current going across, if we think about the units, we have a charge that's going across per time. So charge per time. So the units of current are coulombs per second. And then we just plug this into this equation here. We get V is equal to coulombs per second, ohms on the top. So we get ohms is equal to volt seconds per coulomb. Okay. B, the variables N and P are given in units of meters, or 1 over meters cubed. What can you infer from this? So what do you think 1 over meters cubed means? Yeah, sort of like a volume. Yeah, like per volume, yeah. And what is a variable that corresponds? Oh, you don't, yeah, for this question, you don't really need to know. It's just talking about what does 1 over meters cubed represent. So what's a 1 over volume? So these variables, the 1 over meter cubed, the type of density. So when we think of these variables N and P, where we have N, the number concentration over sort of a density over a volume. And then P is just our, so this is number electron, and then this is number of holes per volume, but this is a concentration. So what that's telling us are concentrations to the number of electrons and holes in the conduction and valence bands. Okay. That's just how you have to think of those variables. And then know that the hole and electron mobility just, some practice. Yeah. So last problem, and then we'll go back to those quiz questions. So note that the hole and electron mobility, mu p and mu n respectively, of a material are independent of doping. So that we discussed that in the previous slide. With this in mind, and based on the data presented on the table, calculate mu p and mu n for gallium and antimony at room temperature. So if that I just want to pull up this table here. So basically, before it said like with an extrinsic p-type, we can sort of ignore like this factor here because it's so much smaller than this factor here. But for this question, I'm not going to do that. I'm just going to write out the description. So for an intrinsic semiconductor, both terms are in the same order of magnitude. We see that here and here. Both are 10 to the 13. And for an extrinsic semiconductor, one term is much larger than the other. So therefore, for p-type, we can typically ignore the conductivity of electrons So since this is a 1 over meter cube and this is a 1 over meter cube, we can typically ignore this value here and then just work with sort of this P contribution. But since we are given the numbers. We can use all values. So then we can write an equation for each case. So for intrinsic, we have sigma equals n q mu n plus q mu p. And then we just plug in 2.5 times 10 to the minus 6 is equal to 3 times 10 to the 13 times mu n plus mu p. So then we can calculate these values here. We get 4.806 times 10 to the minus 6, 2.5 times 10 to the minus 6, and then mu n plus mu p. Okay. And then if we do the p type, we should get another equation where it's 3.6 times 10 to the minus 5 is equal to 4.5 times 10 to the 14 times 1.602 times 10 to the minus 19 mu n plus times 10 to the 12 p. And we can calculate those values. Minus 4 Basically, you can just like stack these two equations on top of each other. And so now you have and you can solve for each one. So you find that mu(n) equal to 0.50 meters squared per volt second, and mu p equal to 0.02 meters squared per volt second. That's how we do that. Let's go back to those quiz questions. What we have. And the answer was so we have N and P. Okay. Sigma is meter. So then from these units we get coulombs per VS meter, and then coulombs per Vs, just 1 over ohm. So we would get 1 over ohm meter. Can you check if this just comes out to 2.4 times 10 to the minus 7? Check on my calculator too. Yeah, okay. That's how you do. This was 1. And then 2. Consider a hypothetical p-type. So p-type, we have an electron mobility of 1400 meters squared per Vs, a whole mobility of 450 centimeters squared per Vs, and then in the dopant concentration of 10 to the minus 19. We have to convert these numbers into meters. Okay, so p-type, you just go back to here. We remember p-type is pq mu p. We ignored sort of pq mu p because this value is a lot bigger than this value. So we just have to make sure that we convert this to meters squared per Vs. About 50, 100. And then on elementary charge, coulombs. And that should give you 2.1627 times 10 to the minus 39. Okay, so can ignore this term since heat type. And then just for mu. Yeah, for sure, yeah. I always post the annotated slides. And like I always put it as a reply to the initial announcement for the slides. So I also posted like number 4 or whatever. So it should, yeah, be under plus like all the recordings and everything. Whenever there's a tutorial that I post an announcement for, I always post a reply with the slides and the recording to that announcement. So yeah, everything should be there. And if we remember this, we get 1 coulomb over Vs meter, which is just over this. Do you have any questions regarding